Welcome student in the lecture series of heat transfer. Continuing with our chapter number 2, it's part 7. Very soon we start our new chapter of this subject. So let's begin the lecture, and here is the content covered during the lecture. Conduction, unsteady state heat transfer or transient heat conduction. Generally the temperature of body varies with the time as well as position. In rectangular coordinates, the temperature is a function of x, y, z and tau, or can say that t, where xyz indicates the variation in x, y and z directions respectively, and t or tau indicates variation with time. In the earlier topics of this chapter, we considered heat conduction under steady conditions, in which the temperature of the body at any point does not change with time. This certainly simplified the analysis, mainly when the temperature varied in one direction only, and we were able to obtain analytical solutions. In this chapter, we learn about the variation of temperature with time and position. If the temperature of a body does not vary with time, it is said to be steady state. But if there is an abrupt change in its surface temperature, it attains an equilibrium temperature or a steady state after some period. During this process or during this period, the temperature varies with time and the body is said to be in unsteady or transient state. The term transient or unsteady designates a phenomena which is time dependent. The steady state is thus the limit of transient temperature distribution for a large value of time. For example, in metallurgy, the heat treating process can be controlled to directly affect the characteristics of the process material. Annealing, a cooling process, can soften the metals and improve the ductility. On the other hand, quenching, a rapid cooling process, can harden the strain boundary and increase the strength. Conduction of heat in unsteady state refers to the transient conditions wherein the heat flow and the temperature distribution at any point of the system vary continuously with time. The transient conduction occurs in cooling of IC engines and automobile engines, heating and cooling of metal billets, cooling and freezing of food, heat treatment of metals by quenching, starting and stopping of various heat exchange units in power installation, brick burning process, vulcanizing of rubber and many more. The temperature field in any transient problem in general is given by T is equal to function of x, y, z and tau. During unsteady state, the change in temperature may follow a periodic or non-periodic variation. First, non-periodic variation. The temperature at any point within the system varies non-linearly with time. Say example, heating of an ingot in furnace, cooling of bars, blanks and metal billets in steelwork, etc. are the example of non-periodic variation. Second, periodic variation. The temperatures undergo periodic changes within the system which are either regular or irregular but definitely cyclic. A regular periodic variation is characterized by a harmonic, sinusoidal or non-sinusoidal function, and periodic variation by any function which is cyclic but not necessarily harmonic. Say example, cylinder of an IC engine building during a period of 24 hours, surface of earth during a period of 24 hours, heat processing of regenerators. The transient heat conduction problems may be solved by the following methods: analytical method, graphical method, analogical method and numerical method. Let's move to our next topic, lump parameter analysis. In heat transfer analysis, some bodies are observed to behave like a lump, whose interior temperature remains essentially uniform at all times during a heat transfer process. The temperature of such bodies can be taken to be a function of time only. Heat transfer analysis that utilize this idealization is known as lump parameter analysis, or say that lump system analysis, which provides great simplification of in certain classes of heat transfer problems without much sacrifices from accuracy. Generally, all solids have a finite thermal conductivity and there will be always a temperature gradient inside the solid when heat is added or removed. But for solid of large thermal conductivity with surface areas that are large in proportion to their volume like plates and thin metal wires, the internal resistance L by Ka can be assumed to be small or negligible in comparison with the convective resistance 1 by Ha at the surface. The process in which the internal resistance is assumed negligible in comparison with its surface resistance is called Newtonian heating or cooling process. The temperature in this process is considered to be uniform at a given time. Such an analysis is called lump parameter analysis because the whole solid whose energy at any time is a function of its temperature and total heat capacity is treated as one lump. Let's learn lump parameter analysis with some example. The simplest situation is an unsteady heat transfer process is to use the lump capacity analysis. Consider a small hot copper bowl coming out of an oven. Measurements indicates that the temperature of the copper bowl changes with time, but it does not change much with position at any given time. Thus, the temperature of the bowl remains uniform at all times, and we can talk about the temperature of the bowl with no reference to a specific location. Now let us consider a large potato put in a vessel with boiling water. After a few minutes, if you take out the potato, the temperature distribution within the potato is not even close to being uniform. You can easily verify this by taking the potato out and cutting it in half. You will see that the outer parts of the potato are well done while the center part is barely warm. Thus, the lump system analysis is not applicable in this case. Let's develop the formulation related to the topic. Let's learn the lump parameter analysis mathematically and derive some equation. Let us consider a body whose initial temperature is Ti throughout and which is placed suddenly in ambient air or any liquid at constant temperature Ta as shown in figure. The transient response of the body can be determined by relating its rate of change of internal energy with convective exchange at the surface. So here in the right hand side of this figure, a negligible internal resistance body or a system is given. It is placed in one control surface and here the energy out is shown and is equal to Q convection. So mathematically we can write the Q heat transfer is equal to minus rho Vc into dt by d tau is equal to HA delta T that is temperature difference T minus TA. So this equation as equation number 1 where rho is the density of solid kg per meter cube. V is the volume of body in meter cube, C is the specific heat of the body in joule per kg degree centigrade, H is unit surface conductance, watt per meter square degree centigrade, T is equal to temperature of the body at any time in degree centigrade, A is the surface area of the body meter square, TA is the ambient temperature in degree centigrade and tau is equal to time in second. After rearranging the equation and we are integrating that, so integration of dt by t minus ta is equal to minus HA with suffix S represent the surface area of the body divided by rho Vc integrate delta T or d tau. Here say equation number 2. Here rho Vc shifted to the right hand side and that temperature difference shifted to the left hand side. So here the integration of 1 upon T, that is say ln T. So here 1 upon T minus Ta. So after the integrating we got the ln T minus Ta. Here integration of 1 d tau is say T. So equation is in the right hand side is minus Ha inside rho Vc multiplied by tau plus constant of the integration C1, say equation number 3. Now for solution of this equation or finding out the value of constant C1, let's apply the boundary condition for the equation number 3 at tau is equal to 0, T is equal to Ti, the initial surface temperature of the body. So if we are putting the tau is equal to 0 and T is equal to Ti, so that term is equal to 0 and so that C1 is equal to ln Ti minus Ta from the equation number 2, we can write ln T minus Ta is equal to minus Ha divided by rho into V into C multiplied by tau plus ln inside the bracket Ti minus Ta. Here substituting the value in equation number 3, then we get T minus Ta divided by Ti minus Ta is equal to the temperature difference represented by theta. So T minus Ta represented by theta and Ti minus Ta represented by theta with suffix I is equal to e raised to inside the bracket minus Ha divided by rho Vc into tau, say equation number 4. The equation gives the temperature distribution in the body or Newtonian heating or cooling, and it indicates the temperature rises exponentially with time as shown in figure. Here the figure shows the time is on x direction and the temperature is on y direction. The exponential heating is the graph of exponential heating going upward when the time increases as well as the temperature increases. The cooling curves going downward when the time increases and temperature increases. The quantity rho Vc divided by h into A has the dimensions of time and is called thermal time constant, which is denoted by tau suffix th. Its value is indicative of the rate of response of a system to a sudden change in its environmental temperature. How fast a body will respond to a change in environmental temperature. So, tau suffix th is equal to 1 upon Ha multiplied by rho Vc and is equal to Rth multiplied by Cth, where Rth is equal to 1 upon Ha, that is the resistance to convective heat transfer, and Cth is equal to rho into V into C is equal to lump thermal capacitance of the solid. The figure shows that any increase in Rth or Cth will cause a solid to respond more slowly to change in the thermal environment and will increase the time required to attain thermal equilibrium when theta is equal to C. The power of exponential Ha by rho Vc into tau can be arranged in dimensionless form as follows. Ha by rho Vc into tau is equal to Hv by Kas multiplied by As square into K divided by rho V square into C multiplied by tau. So we get the value H into LC divided by K multiply by alpha into tau divided by LC square. Here alpha is equal to thermal diffusivity is equal to, we know that, K by rho into C, and LC is equal to characteristic length and is equal to volume of the solid V divided by surface area of the solid AS. The non-dimensional factor H into L, characteristic length LC divided by K, is called the Biot number and symbol is Bi. The non-dimensional factor alpha T by LC square, characteristic length square, is called the Fourier number and the symbol is F0. The values of the characteristic length for simple geometric shapes are given below. For the flat plate, the characteristic length is equal to V divided by A. So here volume is length into width into height divided by area 2 into BH. So is equal to L by 2 is equal to semi thickness, and as I said, L, B and H are the thicknesses, width and height of the plate. For the cylinder, long cylinder, the characteristic length is equal to again V by A, where the volume is pi r square into L divided by area is 2 pi r L. So by the mathematical simplification, we get characteristic length is equal to r by 2, where r is the radius of cylinder. For the sphere, the characteristic length or the ratio of volume divided by area is equal to 4 by 3 pi r cube divided by 4 pi r square, and after the mathematical simplification we get the characteristic length for sphere, that is r by 3, where r is the radius of sphere. For the cube, characteristic length is equal to ratio of volume by area, that is L cube by 6L square. So we get the characteristic length L by 6, where L is equal to side of cube. The Biot number. Already we derived the equation for the Biot number, that is HL by K, where K is the thermal conductivity, L is the characteristic length and H is convective heat transfer coefficient. So the Biot number, it gives an indication of the ratio of internal conduction resistance to the surface convection resistance. When the value of Biot number is small, it indicates that the system has a small internal or say conduction resistance, relatively small temperature gradient, or the existence of practically uniform temperature within the system. If the Biot number less than 0.1, the lump seat capacity approach can be used to advantage with simple shapes such as plates, cylinders, sphere and cubes. The error associated is around 5%. Fourier number, it signifies the degree of penetration of heating or cooling effect through solid. Using non-dimensional term, equation 4 takes the form of theta upon theta I is equal to T minus Ta divided by Ti minus Ta is equal to e raised to minus Bi into F naught, where Bi is the Biot number and F naught is equal to Fourier number. Let's learn about the example based on the topic. A 50 cm by 50 cm copper slab 6.25 mm thick has a uniform temperature of 300 degrees centigrade. Its temperature is suddenly lowered to 36 degrees centigrade. Calculate the time required for the plate to reach the temperature of 108 degrees centigrade. Take density is equal to 9000 kg per meter cube, C is equal to 0.38 kilojoule per kg degree centigrade. Thermal conductivity K is equal to 370 watt per meter degree centigrade and H is equal to 90 watt per meter square degree centigrade. So first of all calculate the surface area of the plate, and considering the two sides, that is multiply by 2, and here 0.5 multiply by 0.5, that is L into B. sides of the copper slab convert into the meter. So we get the area of this plate or slab is equal to 0.5 meter square. Then calculate the volume of plate. V is equal to L into B into H. So that is 0.5 into 0.5 multiplied by 0.00625. Here the thickness is given 6.25 mm, convert into the meter, so we get 0.00625, and by the mathematically calculate we get the volume of 0.0015625 meter cube. After that, let's find out the characteristic length. So characteristic length is equal to volume divided by surface area. So is equal to 0.0015625 divided by 0.5, and we get 0.003125 meter. Then find the Biot number. We know that Biot number is equal to H into L, characteristic length divided by K. So H is equal to given 90 multiplied by characteristic length divided by conductivity also given 370. So we got the value of Biot number is 7.6 into 10 raised to minus 4. Since the Biot number is less than 0.1, hence the lump capacitance method, Newtonian heating or cooling may be applied for the solution of the problem. The temperature distribution is given by T minus Ta divided by Ti minus Ta is equal to e raised to minus Ha divided by rho into V into C multiplied by tau. Substituting the values we get, T is equal to 108, atmospheric temperature is 36, and Ti is equal to 300. And after putting the remaining data, H is equal to 90, surface area is 0.5, density is 9000, volume is 0.001565, and the specific heat is equal to 0.38 multiplied by 1000. So by the mathematical simplification, we get 0.2727 is equal to e raised to minus 0.00842 into tau. So 0.2727 is equal to 1 upon e raised to 0.00842 into tau is equal to 1 upon 0.2727 is equal to e raised to 0.00842 into tau. So finally, after the mathematical calculation, we got 1.2994 is equal to 0.00842 into tau, and so that tau is equal to 154.32 seconds. Let's learn the second example based on the topic, and the data is a steel ball of 50 mm diameter and at the temperature 900 degrees centigrade is placed in atmosphere of the 30 degrees centigrade. Calculate the initial rate of cooling of ball in degrees centigrade per minute. Here the density of the ball is given 7800 kg per meter cube and the specific heat is 2 kilojoule per kg degree centigrade for the steel, and taken the convective transfer coefficient is 30 watt per meter square degree centigrade. Neglect the internal thermal resistance. So let's start the solution with the calculating first radius r. So r is equal to 50 divided by 2, 50 is the diameter. So we got the radius r 25 mm and is equal to 0.025 meter. Ti is equal to 900 degree centigrade, T with suffix A, atmospheric temperature 30 degree centigrade, density 7800 kg per meter cube, and the others are C, H, and tau is equal to 1 minute is equal to 60 seconds, because we want to find out the initial rate of cooling of the bowl in degree centigrade per minute. We know that the temperature variation in the bowl with respect to time, neglecting the internal thermal resistance, in given by T minus Ta divided by Ti minus Ta is equal to e raised to inside the bracket minus Ha divided by rho Vc into tau. So here first calculate the H into A divided by rho Vc into tau. So here area surface area of the ball, that is pi r square, and the volume of this steel ball is equal to 4 by 3 pi into r cube. By the mathematical simplification, we get 3 into h into tau divided by rho into capital R into C. Putting the value of h is equal to 30, time is equal to 60 second, density 7800, R is equal to 0.025, and multiply by 2 into 1000. So we got 0.01385. Substituting the values in the equation, and we get t minus 30 divided by 900 minus 30 is equal to e raised to minus 0.01385. For the positive power, we are solving it by 1 upon e raised to 0.01385 and is equal to 0.9862. So we want to value of t, so t is equal to 30 plus 0.9862 multiplied by 900 minus 30 and is equal to 888 degree centigrade. We want the rate of cooling, so is equal to the difference of 900 minus 888, so is equal to 12 degree centigrade per minute is our required answer. Move to the another example. An average convective heat transfer coefficient for the flow of 90 degree centigrade air over a flat plate is measured by observing the temperature time history of a 40 mm thick copper slab. Density is 9000 kg per meter cube, specific heat 0.38 kilojoule per kg degree centigrade, thermal conductivity is 370 watt per meter degree centigrade. Is exposed to 90 degree centigrade air. In one test run, the initial temperature of the plate was 200 degree centigrade, and in 4.5 minutes the temperature decreased by 35 degree centigrade. Find the heat transfer coefficient for this case. Neglect the internal thermal resistance. So atmospheric temperature is 90 degree centigrade, L is equal to 40 mm or 0.04 meter, density 9000, C 0.38, temperature is 200 degree centigrade, so T is equal to 200 minus 35, 165 degree centigrade. Time is given 4.5 minutes, so is equal to 270 seconds. First of all, calculate the characteristic length. L suffix C is equal to L by 2 for the flat plate and is equal to 0.02. We know that the temperature distribution T minus Ta divided by Ti minus Ta is equal to e raised to inside the bracket minus h into A divided by rho Vc into tau. First we solve this bracket and then we move forward. So h into A divided by rho Vc. So here h divided by rho into V divided by A into C. So we know that volume divided by area is the ratio of characteristic length, so that h by rho into C into characteristic length. Putting the value of rho, C and L, so we get 1.462 into 10 raised to minus 5 into h. Here we want to calculate the convective heat transfer coefficient h. So now putting this value is at here, so T is equal to 165, Ta is equal to 90 and Ti is equal to 200, and then Ta is equal to 90 is equal to e raised to minus 1.462 into 10 raised to minus 5 into h multiplied by time 270 second. By the multiplication we get e raised to minus 0.003947 into h. For the positive power, converting that 0.682 is equal to 1 upon e raised to 0.003947 into h. So finally we get the value of h, and that is equal to 96.9 watt per meter square degree centigrade, our answer. So it's the end of part number 7. We will meet in our next part with the new chapter of the subject heat transfer. So thanks for watching, keep learning, and wish you good luck to all.